In the event you're ever spelunking in the parallel computing literature, you will come across a variety of other kinds of networks besides rings and meshes and tori. I want to mention a few here in passing. The first is a tree network. The compute nodes are the leaves of the tree. The interior nodes are just routers. So you can assume these higher level nodes in the tree are just moving traffic. They don't do any actual compute. Now in this example, these three nodes at the top are binary, but they needn't be in general. Now what about the network properties of a tree? A tree with p compute nodes at the leaves will have p links. It'll have a diameter of log p, and it will have a bisection width of just one link. The scaling of links and diameter is very good, but the scaling of bisection width, being just a small constant, is terrible. The bisection width is poor because to cut the network in half, all I have to do is cut one of these links near the top. Now in practice, network designers typically fatten up the bandwidth as you move toward the top of the tree. Here's an example. At each higher level in the tree, I put a lot more wires to help carry more traffic. This variation on a tree network is sometimes called a fat tree. Fat trees are quite common in medium-scale cluster environments. By medium size, I probably mean on the order of thousands of nodes today. Another kind of important network is a natural extension of 2D meshes and tori. The extension is to higher dimensions. A d-dimensional mesh or torus is basically a high-dimensional cube that is, say, the dth root of p nodes per edge. If the object is a torus, then it will have these properties. Naturally, these values depend on the number of dimensions in an interesting way. For example, the diameter decreases by the dth root of p. So that's good, because as you increase the dimension, you'll decrease the diameter on the one hand. On the other hand, the diameter also depends linearly on d. So as you increase the number of dimensions, the diameter goes up. Now, d-dimensional meshes and tori are very important in practical high-end computing systems. In fact, many of the world's top supercomputers use low-dimensional toroidal networks. As of the time of this recording, there's even one that has a dimension of 6. Related to meshes and tori is a type of network called a hypercube. Whoa, easy there, fella. Very roughly speaking, a hypercube is a log p dimensional torus. More specifically, a p-node hypercube has these properties. It has p log p links, it has a diameter of log p, and it has a bisection width that scales like p. Compare the hypercube and torus formulas. The hypercube is much more expensive in terms of the number of wires, but it has a lower diameter and a much larger bisection width. So what does a hypercube look like? The easiest way to explain it is by visual construction. A hypercube is parameterized by a dimension little d. The number of nodes is a power of 2 in d. The smallest hypercube occurs when d is equal to 0. It's just a single node. To make a one-dimensional hypercube, start by making 2 copies of the lower 0-dimensional hypercube. So here are 2 copies. You then connect the corresponding nodes of the 2 copies. So that's a one-dimensional hypercube. What about d equals 2? Again, start by making 2 copies of the lower one-dimensional system. Then connect the corresponding nodes of the 2 copies. For a higher dimensional hypercube, just keep repeating this process. Make 2 copies, then connect the corresponding nodes. For d equals 4, you do the same thing. 2 copies, connect the links, voila. From this construction process, I hope you can easily see that the bisection width is just p over 2. That's because you just build the larger network by connecting the corresponding nodes of the smaller network, each of which is half the size. Now these days, a hypercube network is more of a historical, intellectual curiosity than something people actually build. There's a lot of elegant theory around them, and you'll see lots of algorithms designed for them in the literature. Now these have just been a few examples of network topologies, which is a very active area of research. I'll put some more references to some recent ideas in the instructor's notes.